Good afternoon. So we are now at a crucial stage of our discussion of the mathematics of SDEs. Okay. We have more or less covered the first objective of the course, right, which was to understand, or rather the second one, which was to understand what is an SDE mathematically, how do we understand it, how do we deal with the white noise, right, etc. And we've seen ultimately that one has to define what a stochastic integral is by choosing where to evaluate the integrand. And in that process, we have focused on two kinds of SDEs, right? The Ito and the Stratonovich. And in the last class, we saw how the Ito definition simplifies things and allows us to derive the Ito mnemonics, which makes it easy to get transformation rules to convert an SDE in a variable x to, for example, a variable y equal to log x. Right? And we also saw in that process how the Stratonovich SDE transforms according to the usual rules of calculus. And together, this helps explain why we work with these two types of integrals, right? Because when you model physical processes, you are really looking at the vanishing correlation time limit of some correlated process, right? And as long as the process is correlated, you would expect normal calculus to hold because it's just like an ODE. It's only when you take the white noise limit that its character changes, right? So you would want to choose the SDE which behaves like a normal ODE. So then that's where Stratonovich plays an important role in the physics. But now when we want to prove things, derive numerical schemes, etc., we can't do that with Stratonovich because all our rules, mnemonics, etc., work only for Ito. So where we are now is we need to find a way to go from Stratonovich to Ito and vice versa. All right. So that's what we're going to start with. So how does one go back and forth, right, between Ito and Stratonovich? Okay, because if this is possible, then I can do all my mathematical development and numerical schemes, etc., for Ito, knowing that I can take any Stratonovich equation and convert it. Okay. Apart from things like numerical schemes, such a conversion is important for the reason we saw in the last class, right, where we looked at the Stratonovich case, right, and we saw that in the Ito case, one has a simplified situation because if you look at an Ito SDE, you take the mean, right? Immediately you get that the behavior of the mean is simply a deterministic drift. Okay, so just by looking at the Ito SDE, you know how the average, what the average behavior will be, right? It will just be an ordinary differential equation which is moving with the drift velocity, whatever the drift is in the Ito, because the noise part will average out, right? And therefore, this means that if you're interested for a given process x that is governed by some Ito SDE, if you want to know any moment of x, all you have to do is transform the Ito equation for x to the Ito equation for x square and take the average, right? And whatever transformed drift you get in the equation for x square, that will tell you how the average will behave in time. Okay? If it's something time dependent, if the drift is time dependent, then you will get nonlinear behavior, etc. Okay? So analytically, you can see how any moment would behave, for example, or any function of the process x will behave if you have the Ito SDE, because you just have to transform it using the Ito formula that we derived, and then just look at the mean. Okay? So that mean of that transform quantity could be some moment, for example. Whereas in Stratonovich case, you can't do this, right? Because if you have the Stratonovich SDE, you take the mean, the noise term does not vanish, right? It will correlate. The noise correlates with the integrand because the integrand is evaluated at the half point. Okay? So the Stratonovich SDE doesn't reveal anything immediately. Okay? You have to kind of simulate it. Right, so if we can do this conversion, it's great because I can start with my Stratonovich SDE, which is modeling the physical process, and then I can transform it to Ito, and then use the Ito equation to directly get information on the process, any function of the process, etc. Okay, so for all these reasons, it's important to go from the Stratonovich to the Ito. Okay, so let's see how to do this. Now our starting point has to be the Ito equation because it's only for an Ito SDE that we know all these mnemonic rules, right, and where we can have hope to make progress. So let's begin by, so consider, right, a process x of t that is governed by a Ito SDE, right, which is the usual form we take. Right? Note the absence of the circle, right? So it is a standard Ito SDE. Again, a and b can be functions of x and t. Sorry, so in the last few classes, I have been a little careless with capital X, small x. When I'm talking SDE, I'm always using capital X, right? We're looking at trajectories. But yeah, I've been a little careless with it, but what I really mean to have is still capital X. Okay, so let's say we have this process, right? And it's governed by the Ito SD. What we want to do is somehow see whether this process has a corresponding Stratonovich equation, which may have some different form. If we can discover this, then we can always backtrack. I can't start with Stratonovich and try to find the Ito because I don't know what to do with Stratonovich. I don't have any useful rules. But I can certainly do the forward thing and then maybe something will be revealed. Okay. So let's see, let's start with this process. Right? Now, what I want to do to understand Stratonovich is to understand how the B circle dW behaves. Right? So we knowing that X follows this, right? Let us now analyze, right, what is happening here. Okay, this is a Stratonovich integral. Okay, let me be careful. Okay, so this is a Stratonovich integral, which I can always define. It is just an integral. The important point is that the x sitting inside, sorry, small b. Okay, the x. So b is also some function, right? It could be sine x, for example. Right? So I can always say that I want to consider or analyze or determine the behavior of this integral, where b is some function of x. I can always say that. And the integral is defined in the Stratonovich sense. So b will be evaluated at the midpoint in the partial sum. The unique important point is that the x on which b depends is governed by the Ito SD. Okay. So it is a Stratonovich integral, but where x is following an Ito SD. That's the important thing. X is right now not following a Stratonovich SD. Okay. But because x is following the Ito SD, you will see that I can use Ito mnemonics in a second. Okay. So let us start here. Now we know that this is, right, by definition, the mean square limit. So this stuff is equal to the mean square limit of the partial sum, right, where n goes to infinity. Right, and what is in the partial sum? B will be evaluated at x I minus 1, correct, plus dx, so delta x, sorry, correct, into the delta wi. Yeah, that's by definition. And now I can Taylor expand the B, it is just some function. So if I look at what's happening in this partial sum, correct, plus dou B by dou x now here I can use small x. This is at I minus 1 times delta x by 2. Okay. This is fine. So I have taken the partial sum, which is just the definition, right? Use the definition of the Stratonovich integral, then done a Taylor series. And now I need to know how delta x behaves with delta wi. Right? But that I am going to use my Ito SD and substitute back. Right? So I'm going to use 1 for delta x and the Ito mnemonic. Right? Right? So what's going to happen is I'll get an A delta t, right, sitting here instead of delta x, and I'll get a B delta w. Okay, now the A delta t, when I multiply with delta wi, that will go off. Right? We know from, we proved it in the Ito mnemonic, right, that in the partial sum delta t delta wi with any non-anticipating function evaluated at the beginning will vanish, right, as n goes to infinity. We've already seen this. Right? So the delta t will not contribute anything because it's like delta t delta w, right? This drops out. The only thing that will contribute is the second term because that will give me delta wi squared, which will become like delta t by 2. Okay, so I substitute this in and use the mnemonic and recover the integral. Right, I will find that it is equal to Let me do the partial sum still. Right, the first term will survive. And now in the second term, I'll have dou b by dou x times b, right, which is coming from here, by 2, which is in the denominator, right, and then I'll just get delta wi square. Okay, but that I know is the same as delta t. That's the Ito mnemonic. Okay, and other terms will drop out. So I can just put delta t here. And this is evaluated again at xi minus 1. Okay, and then I recover, again, this is the mean square limit, etc. And then if I pull it back into integral form, you see now this is an Ito integral. Yes, because I'm evaluating b at the starting point. This anyway doesn't matter because I've got delta t now. It's a deterministic integral. So I will get an Ito integral b dw, so no circle, right? Plus now a nice deterministic integral. Okay, so what we have shown now is if I have x, okay, that satisfies an Ito SD, and I look at the Stratonovich integral involving some function of x, okay, I can prove that this Stratonovich integral is equal to the Ito integral of the same function, right, b dw, plus a deterministic integral, right? This we have shown. So this integral is nothing but what is there in this SD, right? So remember, an SD is nothing but a notation, right, for an integral. So x is equal to, x at t is x naught plus this integral a dt plus integral b dw. So this is the stuff that would come, is the same as this term in the SD form, right? What I have is this extra drift, correct? So what it means is, suppose instead of this Ito equation, suppose I had the extra drift term sitting in the SD, I could take that drift term with this term and rewrite it like this. Okay, so that gives us the conversion, right? So what we have shown, right, this means that the Ito equation, right, which is a modification of this, right? So now this I used to prove this, right? Now I'm saying something separate. Okay, so if I consider an Ito equation which has an extra drift, right, that this is equivalent to so I can merge this and this, right, these two, which again, this is just notation for integrals, right? So this is an integral, this is an integral. I know their combination is the Stratonovich integral. Okay, and this is Stratonovich. Okay, so what we have done is, we are saying, I mean, that is the whole point, right? That I have a process X, it can simultaneously satisfy an Ito equation and a Stratonovich equation, but they will be different. Okay, and the connection is shown here, right? Because we have seen for some Ito SD, right, an X defining an Ito SD, you can convert a Stratonovich integral to an Ito integral plus a drift, right? Which means by anticipating that drift, if I had so if instead of A here, right, I had some A prime plus that, it would give me the Stratonovich equivalent with A instead of A prime. This is the logic. Okay, so all you have to do is adjust the drift. So if I have Ito, this Ito, I will get the corresponding Stratonovich, right? Or a Stratonovich of this form will be this Ito with the extra drift. So then, of course, you can do the backward, right? So suppose, right, and similarly, right, by going backward, an Ito equation with the minus stuff, right? So this is just now using this formula in back reverse, right? That this is equivalent to the following Stratonovich in the standard form. Sorry, the other way around. Okay. So because I know the Stratonovich, when I go to Ito, gives me an extra drift. If my Stratonovich started out with a deficit of that same drift, then when I go to Ito, I'll get the usual Ito. Okay, so it's just going back in reverse. Okay, so that's neat. Any questions? So now you can see that this anticipates what we had seen in the last class, right? That when you have the Ito equation, you take its average, the drift tells you how the mean behaves, whereas you can't do this with Stratonovich. And that very fact means that if I have a same process governed by both an Ito and a Stratonovich equation, right, there has to be some extra drift in the Ito, because in the Ito case, only the drift tells you how the mean evolves, and the noise averages out to 0. Right? Whereas in the Stratonovich, the noise does not average out to 0. So in other words, the fact that the noise doesn't average to 0 means that the noise is in the average giving you some drift behavior, right? And that gets captured when you go from the Stratonovich to the Ito, because I know that if I take average on the Ito, this will disappear, right? Whereas if I take average here, this does not disappear. So the stuff that does not disappear on average is precisely the drift that appears in the Ito case. Okay, here I should say. It's the fact that this does not average to 0, but this does, is what gives you the drift, right? That stuff that doesn't average out is the drift. Okay, so now, because of this conversion, I can say average of this is nothing but this drift, because I know that these two things are equivalent. Okay, so this is, you can see, quite a simple derivation, but which gives us a very powerful result, because now I can look at any physical process, okay, which is being driven by some highly fluctuating, it could be a fluctuating parameter, it could be a fluctuating force that is being imposed, right? Some aspect of the problem is fluctuating very rapidly for some physical reason. And if I were to study the process on those rapid time scales, then I would have to model everything. But if I zoom out, right, in time and look at it on long time scales, I don't really care about the details of those fluctuations other than to say it looks like something stochastic. I only care about the statistics of those fluctuations, right? And in the simple case, if it's just important, the only important thing in the fluctuations is the standard deviation or the variance, then I can model it with Gaussian noise. So that's where I will introduce or model my physical process with a SDE, but I would have to use Stratonovich, keeping in mind that the actual physical process I'm modeling is actually correlated, right? It's actually just an ODE with a highly fluctuating term in it. I've replaced that with white noise, and so I got an SDE. But if I want my SDE to show the same behavior as the ODE as the time correlation goes to 0, as it becomes more and more fluctuating in time, then I should use Stratonovich. Otherwise, if I transform my equation for x to an equation for x square or log x, I'll get different equations or different behaviors from the ODE model and the SDE model, unless I use Stratonovich. Okay, this is the point. So I have to start with Stratonovich, okay, based on this reasoning. But then the Stratonovich equation, I want to know how the mean behaves. I don't know what to do because of this correlation. And that is precisely why multiplicative noise becomes interesting in physical processes, right? In fact, if you think about it, if you have an ODE system where some of the variables are fluctuating very rapidly, And if those fluctuations depend on the state of your system, it's typically some kind of nonlinear behavior. There's something nonlinear in that problem. Right? And so even though this equation looks linear, right, this multiplicative noise has this nonlinear type character because the effect of the noise depends on the state of the system. And therefore, the fluctuations affect the mean behavior because of some correlation here. Once again, remember, multiplicative noise means where B depends on X. So in that case, this is non-trivial, but I can extract out the effect of these correlations, right, of the multiplicative noise by transforming to Ito, because then this noisy integral has zero mean, and the mean effect comes into the drift, right, as you see here. And that effect is just a simple term, B by 2 times the derivative of B with respect to X. And immediately you see that if B doesn't depend on X, then there is no difference. There is no effect on the mean behavior. That is additive noise. Right? So additive noise just gives you variations. It doesn't affect the mean. Some sense that is like a trivial effect of adding fluctuations. Okay, but if it is multiplicative, it will affect the mean. So that is strongly non-trivial. In other words, if you don't do a stochastic model, you cannot even predict the mean behavior, right, in systems where the noise is multiplicative. Whereas if the noise is additive, you don't need a stochastic model if you're only interested in the mean. Right? Just like in Brownian motion, I don't need to do a model to know that if there's a particle doing random motion, its mean position will be where I started. That is obvious. Yes? What do you mean by multiplicative? Where B depends on X. It means what I was just saying. That the definition is that it depends on X. Right? The implication is what I'm just saying, right? That when it depends on X, you will see that the noise affects the mean behavior, which you can now prove, right? Exactly. Right? Because you will start with this kind of Stratonovich equation, the B depends on X, right? And if I take an average, I know that this average is not zero because these things are correlated in the Stratonovich integral. Right? So what is the mean of this? It's not zero. What is it? You can find out by transforming to the Ito equation, because now this mean is zero. So if I look at the mean behavior of X, this noise will drop out. It doesn't matter what B is. And the effect of that B depending on X comes in here. So you will directly see if I take average, right, of this equation, then you will get the average X evolves like this quantity into time. That's it. It's just moving with that velocity. Will it be? A by 2 or B by 2? B by 2, because this is there. So A doesn't do anything, right? It just it's the same whether it's Stratonovich or Ito. It's just that is just a deterministic part. So the B part is what changes, right? And the B part gives you an extra drift, which you have to account for either way when you go from one to the other. Okay, so this is if you learn nothing else from these lectures, right, you should remember this, okay, that if you are looking at modeling or understanding some kind of fluctuating process, if those fluctuations do not depend on the state of the system, like Brownian noise, right, the fluctuations in the particle's motion doesn't depend on where the particle is in standard Brownian noise. In such systems, you don't need to do any stochastic modeling to find out the mean behavior, because the effect of the fluctuations you add don't affect the mean. That is additive noise. It just adds variations. So the only thing of interest in doing any kind of stochastic model is to look at the variations from the mean. Okay. So as I said in Brownian motion, if you just want to know where is the mean location of the particle, it's just wherever you started with. But now if you say that the fluctuations on its position or its steps depend on where it is, then you have no choice but to model it stochastically. A deterministic equation, right, will not give you the answer, even if there is some non-trivial deterministic dynamics. Right? So I can have a particle which has a mean velocity and some fluctuation. And if those fluctuations are just nice Brownian, don't depend on where the particle is or its velocity or any such thing, then I can just use the ODE taking only the deterministic velocity. That will be the mean position. A stochastic model will just tell me if the mean particle moves like this, it will give me the cloud of positions around it. That's all, but not affect the mean. But now if you say that the fluctuations on the particle, for example, depend on its velocity, okay, which is not unimaginable, right? Some situation like this. A higher speed particle may have larger fluctuations or something inverse, right? Depending on the physical situation. So the moment you say the fluctuations depend on anything about the system's properties, right, that becomes multiplicative because the B depends on the state of the system. And then those noise will influence even the mean, which means that a model that has ignored fluctuations can be completely wrong. Okay, so then you have to do the stochastic model. So this is the crucial point, right? And then how to do it is what we have been doing here. Right? But at least this, if you remember, right, because that's a qualitatively important and crucial thing, right? You cannot ignore the fluctuations if they are multiplicative. So the first question you should ask yourself, if you encounter stochastic phenomena, are the fluctuations multiplicative or not, right? Or is the magnitude of the fluctuation at any time dependent on the state of the system? If it is, right, then even the mean is going to be affected by those fluctuations. And you cannot ignore the fluctuations. Okay. So like this, there is the equivalent version for a vectorial system, right? That's in Gardner's book. It's a standard extension using Einstein notation. Any questions about this equivalence? Okay, so now that we know this, we are now in a good position because it means that I can only study now Ito equations. Because you take any Stratonovich, I can just convert it quite easily to Ito. And so now I can do everything with just an Ito equation, which is much easier to work with. And therefore, what we will do next, which will address the first objective of this course, right, and the big three, is how do I connect an SDE to the Fokker-Planck equation, right, or an SDE equation for trajectories to the diffusion-like equation for the population of all the trajectories or the field. And we will do that starting with the Ito equation. So we've already derived Fokker-Planck equation for stochastic general Markovian stochastic process, continuous stochastic process, right? From thinking about the PDF itself and doing Chapman-Kolmogorov probability balance, etc. Right? Now we will get that same equation starting with the SDE. Again, what we will do is the starting point will be exactly the same as what we had when we derived it using the PDF. Right? So I'm saying that I have the following. Sorry. Okay, and what I want to do is I want to find the evolution equation for the PDF of x comma t. But now I'm using small x here because this is in the probability space, right, where x is a coordinate, and this is a trajectory where capital X is moving around the space of small x. And in the general case, it can be a vector n-dimensional space. Right now we are only in 1D. Okay, but the generalization is easy. Okay, so what we'll do is just as we did in our earlier derivation, we'll start by considering the expectation of some function f of x. Okay, and I know that this can be written as integral right, because the expectation is integral of f into p dx, right, and then I can take the d by dt, I can take the d by dt inside, correct? And when I take it inside, it will not act on f because f is only a function of x by my choice. Therefore, it only acts on p. Okay? So this is equal to this, but it's also equal to, from the definition of this thing, right? The mean of the increment by dt. I have skipped some details, but it's clear, right? So if I look at the evolution of the mean, right, in terms of differentials, it's this change in f, change in the mean of f. So if you want, I should write it like this, right? It's that by dt, right, by definition. Then so that is the same as the mean of the increment in f. And this is important because I know now from the SDE for x, right, you can get the equation for the increment of the function f of x. That is where we'll use Ito's formula. And then I have to take the mean of that. Okay? So I'm going to use Ito's formula for finding this df. So can you tell me what that is? By 2 is there or no? Right? So it's all of this into dt, correct? So you'll remember that so that f is not a function of t. Right? My f is not a function of t, right? Yeah. So applying Ito's formula where f is only a function of x, you have one term that comes from the drift, right? Because I'll do df by dx into dx, right? And that will give me a. This dw is there later, but remember I'm taking the mean, right? So if you look back in your notes to Ito's formula, the dw terms by themselves after I take the mean will of course vanish because it's an Ito SD, right? So the contribution df by dx, the deterministic part will survive under the mean, right? But the b into dw will vanish when I take the mean, right? Because I'm looking at the mean. And then the other part of the drift comes by taking the second derivative of f with respect to x square, 1 by 2 into dx square, right? Where again, using Ito's mnemonics, only the b square dw square term will survive, which under the mean again, I mean, it will become dt. Okay. So you can see the mean of df is just a deterministic part, right? Obviously, the noise, because it's Ito, will vanish. Fine. So now I have to just substitute that. Remember, it's df by dt, so the dt will vanish. And so therefore, what I get is, yeah. It is average, no? That's why it is. Right. So after taking the average, only this stuff will survive. Right? The dw will go off. That's what it means. All right, yeah, what you're saying is correct. So I have to put the ensemble average. When I put the average on the dw terms, right, they will drop out. So should say note that average of anything dw, right, is equal to 0. Okay, yeah. So I do have the ensemble average terms. Right. The point is that this integral is deterministic, right? But one still has to do the ensemble average because you have to find out this is a function of x, right? And I still have to do the average over all the x relative to this PDF. Okay. So now when I'll use a definition of the ensemble average to begin P. So by combining these two, what I now have, yes? Yeah, so we'll see that later. Okay. So I just use the definition of the ensemble average. So this entire quantity, which is just some function of x comma t, that sits here, gets weighted by the p. So now if you look at both sides, this is exactly the situation I arrived at midway through my derivation of the Fokker-Planck equation the last time, right? After using the definition of the first and second moments, etc. Right? So what do we need to do now is we just want to pull the derivatives onto p and bring f out common, right? Because then I can take everything multiplied by f and use the fact that f is arbitrary to argue that the factor multiplying f is pointwise 0. And so I just use integration by parts. This is exactly what we did before, right? In fact, this is the equation, exact equation we obtained at some midpoint of that derivation. So from here, if we do the rest of the steps, by going back to your notes, right, finally you will find that I'll get the following equation, right? Right, so the A will go inside, right, when I do integration by parts, and the minus will survive because I do need one integration by parts here. And here I have to do 2, so the minus will go out, right, and I'll get right, and that's my Fokker-Planck equation, which corresponds to this SD. Okay, and then you can see the diffusion now is b square. That's the important connection. So before I proceed, any questions about this, how we got the Fokker-Planck? Right, so we reach here and then the rest of the steps is just some integration by parts and we follow what we had done before to finally argue that we get the following Fokker-Planck. Okay, now if you look at, so then now we can look back at this connection, right, which was the second objective, so the first objective. So I start with an SD for some kind of Brownian walk, right, where the velocity, the deterministic part, and the Brownian amplitude can be functions of space and time on the system itself, right? And now we see that the velocity part comes in directly in the advection term, so not surprising, right? And the stochastic fluctuation, right, comes in exactly in the diffusion, but where the amplitude is b there, then the diffusion becomes like b square. Right, again, remembering that dw is going like root dt, right? So it's the square of it, dw square, that contributes to the net effect, right? And that's how you get b square also sitting there. So if you were to flip it and say I'm starting with a Fokker-Planck equation where I have velocity a and some diffusion b square or some diffusion d, right? Suppose you had capital D here as the diffusion, then the corresponding SDE should have root d. Okay, that's important to keep in mind. Right, so b is intimately related to the diffusion coefficient. It's just the square root of the diffusion coefficient. And then the factor 1 by 2 will come depending on whether the diffusion equation has a 1 by 2 explicitly. If it doesn't and it is sitting in the d here, then this will be root 2d. Okay, so now if you look at any text that try to say that I have an SDE version of a diffusing particle, you'll often find root d or root 2d. That depends on how the Fokker-Planck is written. Okay. But that's a matter of convention. The important thing is this is the equivalence. And now, okay, so that's nice, but we will now see that if I look at the vector version, there's an interesting property that arises. So often some of the derivations follow very easily from this scalar to the vector version in most cases, but the implications are kind of non-trivial. Okay, I'll show you one non-trivial implication now, but there's also an important nuance when you do multidimensional systems in the meaning of the Stratonovich equation. We'll address this later in the course. Okay, but for now, if I look at this version, I'll have ddt of p. P remains a single function. It's just probability defined on a n-dimensional space, right? So x is a vector. but there's only one probability distribution, okay, of having x1 equal to something, x2 equal to something, x3 equal to something. So this is a scalar, so everything else has to become a scalar, right? And I will have AIP. In fact, this thing will follow, see the nature of this operator is coming from Ito's formula. So if you go back to your notes and see the vectorial version of Ito's formula, that will give you the structure of the terms to follow. Okay? Okay, and then you will have, remember B becomes a tensor in the multidimensional Ito SD. Right? Okay, and this means now, right, and this thing corresponds to okay. So the important point now is that the diffusion tensor, right, right, or if I write it in tensor notation, it's B transpose. Any questions? Yeah, I'll come to that. Okay, so the fact that you now have an n-dimensional SD, it just means that you can diffuse differently in different variables. Right? That's not surprising. If it's a Brownian particle, it means if your diffusion is the same in all directions of space, then this will just be an identity times a constant. It will be a diagonal with all equal entries. But if you have some weird diffusion effects, like you diffuse differently in X, then in Y it becomes anisotropic, right? And there are cross things, this can be a general tensor. Okay, but if you're not doing a Brownian motion in space, you have some arbitrary stochastic process, of course you will have some general tensor here, because if you have different variables in your system, temperature, concentration, etc., or different reactions, right, in a chemical system, each of them can have different fluctuations, depending on the species or whatever. So in general, you'll have different variables diffusing in different ways, right? And then there can be some cross interactions and so on. So you will have a tensor. And that will give rise to a diffusion tensor in the Fokker-Planck equation, which again tells you how different species diffuse in different directions of probability space. Okay. Now what is interesting from here immediately is that because of this nature, right, the same D can be equal to right, for any symmetric unit norm S, right? So in other words, I can introduce any intermediate tensor S, right, which is a rotation matrix. So that is the meaning of those properties, right? So if S is symmetric, then S transpose is the inverse of S, right? So in other words, where S transpose is equal to S inverse. Right? So this is a rotation matrix in terms of physical understanding, right? And that will give me the same diffusion. Right? So that means instead of having a vector B, right, I can replace B by the matrix B with some B times any rotation. And I'll get exactly the same diffusion coefficient. So what does it mean to multiply B with some rotation matrix? Remember where B is, right? So B is basically telling you how each noise that you are adding affects the variables. So suppose I start with a B that is diagonal. That means the Wiener process 1, dW1 only affects x1, W2 only affects x2 and so on, right? Because B is diagonal. But now I'm saying that the Fokker-Planck equation you get for that SD will be identical to the Fokker-Planck equation of a different SD, where I'm making the W2, W3, W4, etc. all affect x1. How? By simply multiplying B with some rotation matrix. So that rotation in matrix X will recombine the different noises in such a way that I'm still normalizing, because that's why S has got unit norm. Okay, so I can recombine the different Wiener processes, right, to affect my variables in a new way, and still I'll get the same Fokker-Planck equation. And this should not be surprising, because after all, some suitably normalized sum of Wiener processes is a Wiener process. Right? I have a Gaussian of some of variance root dt. Right? If I have several such independent Gaussians and I add them up and divide by what I'm adding, right, with suitable normalization, I'll get another Gaussian. So there's nothing to distinguish W1 from some recombination of all the W's, as long as I normalize it properly. That normalization is coming in the fact that the S I'm using, right, is got unit norm. So it's just saying that I can recombine the noises, right? But that SD can have different behavior along trajectory wise, but the PDF will show the same behavior. Okay, so this shows you what we had seen actually earlier in the course also, right? That when you get the Fokker-Planck equation, you lose some information, because it's like you have averaged, right? To derive it, you have looked at the mean of the expectation. So it's, in some sense, it's like coarse graining, it's averaging out, right? You're no longer zooming in and looking at individual trajectories. If you want to know how the distribution of trajectories behave, you are effectively averaging, right? And that process basically tells you that many different kinds of, actually an infinity of them, right? Because S is arbitrary, subject to those conditions. So an infinity of different possible variants of the trajectories which look different on the trajectory level, right? When you average their properties, any kind of average, right, any moment will behave the same, right? So different trajectories can show you the same PDF evolution. So if you don't care about the detailed statistics of individual the detailed behavior of individual trajectories, that means you're not interested in the strong properties, but only in the weak properties of the stochastic system, that means it's statistics, then these changes don't matter, right? Because you'll only be interested in the Fokker-Planck. So it means even if I never calculate the Fokker-Planck, if I'm only interested in using SD and I'm going to simulate the system with SDs, if I'm only interested in statistics, I can transform that SD in some way which may be suitable for my numerics and get the same results. Yes? There is no goal. I'm just showing you that the diffusion Fokker-Planck equation is the same for an infinity of different SDs, that's all. And then how you use that depends on, it's a different situation. Right? But the main point is this, that there is no one-to-one correspondence between the two. It's not unique. Right? An SD, given SD will not have a unique Fokker-Planck. Sorry, a given SD will have a unique Fokker-Planck, but not the reverse. Right? A given Fokker-Planck will not have a unique SD. Right? They can be a whole variation of it. Or at some level, there are properties of SDs which you will never be able to distinguish statistically. The statistics will be the same. Okay, so that's an important point to bear in mind, which then has practical relevance, because when you're designing some numerical scheme, instead of using maybe the noise that is obtained from physics-based arguments, right, you may realize that's difficult to implement numerically. So if I rotate out this P matrix, it may become easier to simulate for some reason, and then I can do that. Just like we had seen earlier that instead of using Gaussians for this, I can use uniform probability distribution, right? So these properties of SDEs people use to derive better numerical schemes, more efficient computing. Right? That's a secondary situation. It's also important in modeling, again, because one has to always bear in mind that certain properties of the SDEs will not reflect in the statistics. Or if you start, in many cases, mathematical modeling or physical modeling starts with a Fokker-Planck equation. And then, because of Fokker-Planck equation, to try to solve this PD in high dimensional space, if X is a vector of many dimensions, is numerically impossible almost. So then instead of trying to get information by solving the Fokker-Planck, you want to derive the equivalent SDE and then simulate the SDE. Right? Then you just simulate enough trajectories, you will get information on statistics. So then how to go from here to there, we now know. But we should remember that this is just one possible candidate. You can get any other number of them. Okay. Anyway, so those are nuances we'll encounter later. But for now, the key message is, given an E2 SDE, I can get the corresponding Fokker-Planck equation and vice versa, which was what we wanted to do in the beginning of the course. So now, if you write down a concentration advection diffusion equation, right, for some species, I can tell you what is the equivalent Brownian dynamics equation by doing the conversion from the Fokker-Planck to the E2 SDE. And if the B is multiplicative, then the E2 SDE will also have B a function of X, right? And then I can get the equivalent Stratunowich also, right? Which will be the actual physics type ODE that is underlying some system, where instead of dW, I have some highly fluctuating noise. Right? So you have the full chain from the Fokker-Planck to the E2 and then to the Stratunowich SDE, and then you can look at whatever you want based on what you want to do. So the assignment 2 that you've been doing is been focused on, so assignment 1 did computations of an SDE before we knew what an SDE was, etc. But if you look back now, you will see that basically you solved a simple SDE. Okay? And you can, of course, adjust that code that you wrote to solve SDE to solve some SDE where B is a function of X or whatever. And you understand why in that code you had to take the variance of the Gaussian as root delta t, right? All this is clear now. So we know how to solve SDEs numerically and what they mean. In assignment 2, you've been solving this Fokker-Planck type diffusion equation, which is something more familiar, as we've always solved these equations in any transport process, right? It's advection diffusion equation after all. So assignment 2 revises this, and you've done some numerical simulations of this equation with different boundary conditions, etc. And assignment 3 now, which will come up later, will be to see a direct equivalence here, right? So what will be very nice, which is what you will have to do, is to solve the SDE for some system, right? Actually get trajectories. You can impose some boundary condition on the SDE. For example, you say X is moving, and then if X reaches some position, X equal to 1, it cannot pass 1. It gets reflected, which you can, of course, implement in a code. And that equivalent, hopefully, the Fokker-Planck is like putting a no-flux boundary condition. And what would be nice is you generate many trajectories by solving SDEs with some appropriate condition. And then you solve the corresponding Fokker-Planck, and you see if actually you are able to get the same behavior. Right? So ideally, you get a solution for the distribution of P. Maybe you start with some Gaussian or some uniform distribution, and you see how it evolves. And then you see if you solve many trajectories, again, suitably placed so that you sample the initial distribution. Right? Let's say you're starting with a Gaussian here. Then the initial position of X should be sampled from that same initial Gaussian distribution. So you have a distribution of initial X's. You evolve all of them. And then you recompute the PDF by doing some kind of binning. That should agree with this. Okay, so we will check this numerically in the assignment. Right? So that will be a nice way to see how these things work. Okay, even in 1D now, if you see, which you can test in that assignment, that this is like saying B square is equal to B into A into 1 by A into B. It's as long as those things cancel out, it will not matter. But so there is also that flexibility there. No, but in that case, you can't do it, right? Because suppose, so let's see in 1D if this has any implication. Suppose I replace B by B into A, not A, okay, B into, I don't know, E or something. Okay. So instead of B, if I had B into E, then it will give me B square E square. Right? So the diffusion would be, and the only way I will have the same diffusion coefficient, right, is that E square should be 1 then. But that just means E should be 1. Okay, so the fact that this is B square, right, it doesn't allow you to vary this, right? Because it tells you that if you multiply it with E and you require the same diffusion coefficient, that whatever you multiplied, E square should be 1, which is only going to force you to be 1. The reason you have something different here is because in multidimensional space, you have the freedom to rotate. Okay. So in 1D, the equivalence is unique, but not in multi-dimensions. Okay, any questions? I wrote orthonormal there just to, it's okay. The eigenvalues of the S are orthonormal, right? I mean, just the point is it's symmetric and normalized. Okay. Fine, so good. So we have now come to the end of our mathematical discussion of SDEs, and we have all the basic tools. Okay, we need to now start studying physical systems. So from the next class, we'll try to use these ideas and look at some examples, right, and gain some more understanding and move towards physical applications of these ideas. Right? And after the mid-sem especially, we'll start moving towards the third part of the course, which is turbulent flows, and how these ideas can be applied there. Okay, so we'll stop with that. Thanks, everyone.